In the name of the Almighty, the Compassionate, the Merciful. Now we come to our last lesson concerning the applications of derivatives, which is curve sketching. In fact, this is one of the main concerns of students. Of course, students have other concerns than curve sketching, but in fact, they usually ask the traditional question, should one always have to draw the graphs of functions pertaining to a certain problem? Indeed, this is not actually difficult, so long as you follow a set of conventional or systematic procedures. They only think that machines only can do that. But in fact, this is not the case. All you have to do is to follow certain rules, and especially that you are not really requested to do complicated graphs. All you need is a kind of schema, or like they say in French, croquis, some kind of crude idea of how the function behave. In other words, what is the maximum, what are the local maxima, minima, what are the inflection point, etc., the asymptotes. So in fact, in this lesson, we are going to explain and display those methods which are relevant to drawing graphs of curves. Especially that even if you use softwares for doing that, of course you may use calculators, but calculators you don't get neat drawings. But in order to get neat ones, you need to know the code of softwares, and codes are in fact difficult. So today we're going to explain a few of the techniques which are very simple techniques in order to draw graphs of curves. So concerning the sketching of graphs, first we are going to speak about the Cartesian representation of graphs, and then the drawbacks of mechanical drawing, which we mean machines, and then the graphical properties of functions, and then the steps for drawing graphs. These are actually the subject we are going to speak about. First of all, we wish to understand what's the meaning of graphing. Graphing, it's to mean that the meaning of graphing exactly is to be able to track the behavior of functions. How do they increase, decrease, etc. In other words, to display their properties, to track the features of such functions in a certain interval. If you x vary in a certain interval, so you get a corresponding value of y, and from this you move onward. So in fact, the graph sketching is to draw to the curve of the function y is equal to f of x for example, if you are concerned with the orthogonal axes, which are the Cartesian ones, and this to track the behavior of f of x when x changes its value in a given interval. In order to do this, what you practically do is that you draw two orthogonal axes. This is actually the what was proposed by Descartes, and then you give some values of x which pertains to the domain of the function, and then you calculate corresponding values of y. And then what you do is that you enumerate all these order pairs from 1 to n. You choose n points, for example, and you locate these points, p of xy and iy, on the plane xy, bounded by these orthogonal axes, which are ox and oy. And then, from then, what you do is that you may connect these points together. You connect them by straight lines, just straight lines. And when you connect them with straight lines, you get the curve of the function. And of course, the more you take the more you take, if you take more points for x, of course you reach a better accuracy. Of course, if you feel that there are places or there are regions in which you wish to understand more the behavior of the function, then you may take more points in these regions. So you assign more points to the independent variable x, and as I said, it improves your representation. For example, suppose we wish to sketch the graph of y is equal to x squared from 0 to 3. Now, suppose we take n equal to 7. We start by n equal to 7. So all you do, you calculate the value of y using a simple calculator, and you tabulate this for each value of x from x equals 0 to x equal 3. In other words, you take 7 points and you calculate the corresponding values of y, and then you locate these points on the plane xy, and then you connect them by points. You notice here that the curve is not smooth. Why? Because the number of points is small. In fact, you need to increase the number of points. In other words, although your function is known to be a differentiable function, which is x squared, it doesn't look it here this way because the number of points you took a small number of points. Suppose you take n is equal to 13, you increase the number of points, so you may end up with a better representation. This one is smoother. It improves with n. The more you take more number of points, and the better you obtain a better accuracy or a better representation of your function. Of course, there are odd situations, in fact. Personal computers can do this, which is simple. Personal computers, as well as calculators. All these calculators, which are a little bit advanced, they are called sketching calculators, graphing calculators, they can do this. But as I said before, you have to know the code. Not for calculators, of course, because calculators are simple. They don't show you a neat representation of the graph. You need to use some software. And softwares, there are, of course, there are many commercial packages in the market, but if any of them, in order to get a neat representation of your graph, you need to assign many things. Of course, first you have to give it the function f of x, and then you need to assign the range, the plot range. It's called the point for x and y. Again, you need to decide whether the graph should be thick or thin. The aspect ratio, which is the ratio between how the base or how the scale x look like corresponding to the scale of y. If you need to draw circles, again you have to upload load some other package, some other subroutine, for example, in order to draw squares. Or for example, you need to connect lines between 2 points, and these lines can be intermittent or can be straight lines, unbroken, and these so you see, you need to, for example, you need to write on the to type the relation your f of x, etc. All these or you need, for example, to either to keep the ticks, which are the scale 1, 2, 3 on the x-axis and on the y-axis, or you need to remove it. So all this may need from you quite a lot of writing lines and writing code, which is difficult. So and in fact, even if you know all this, you assign the plot range and the aspect ratio on the curved shape, etc., whether continuous dash or intermittent, there are actually odd situations in which you feel that you get drastic representation. Like, for example, this one. You need, for example, to represent the graph of x divided by x squared minus 3 squared. And we take n is equal to 11. For example, here, when you take n is equal to 11, and your domain ranges for example, from -6 to 6, and then you connect these lines together, these order pairs together, you end up with a graph of this sort. And actually, this is far from the true graph. Why? Because you see that the point x is equal to square root of 3 or minus 3 are asymptotes. Because you didn't meet this point, you didn't take this point into consideration, you skip it, you skip this point, so you get some crude one which is far from being true, and whereas the true representation look like this. So you see now, if you assign points and you miss a certain range of points at which you need to clarify the behavior of the function, you may end up with a wrong actually representation of your graph. And even if you take more points, it amounts to the same, because you may not even end up with choosing a point which is actually gives you some good representation of how the graph looks like at this particular point. So you have to be cautious in a way. And this is why, since the idea of drawing graphs is not to make it so precise as one wishes to, using mechanical machines. All you want is to really exemplify, to clarify those particular features of this function. So these mechanical, in fact, techniques may lack capabilities for some reason or the other. For example, they could not tabulate all the points, as we have seen. Again, they could not clarify the behavior between these chosen points. For example, when we skip the point square root of 3, we couldn't reach a point which is important for us to understand the behavior of the function around this point. Again, scanning the whole domain, it restricts itself because since you assign to the code or to the software a certain range from where on which you need to draw your graph, and so actually you are located in a certain region only. You should expand it on the whole range of the function. Since it restricts itself to a certain range, this range in fact might not show all the properties that you may wish to know about. What we are going to really to speak about now, what are the graphical properties? In fact, these mechanical machines or these software, not only that they don't help you 100%, but also for simpler functions, it would be a shame also to use these machines. You should know how to draw simple graphs. For example, if you consider something like this, x over x plus 1. Or suppose, for example, you get minus 2x, for example, plus 1 divided by x plus 3. Or, for example, x divided, for example, by x squared minus 1. It would be really a shame to use machine to draw these, the graph of these functions. Because actually, all you need to do is that these graphs have simple properties. For example, the first one here, this is x and this is y. You reach for the properties which are so simple to notice. Here you notice directly that x is equal to minus 1 is a vertical asymptote. And when x gets very large, this one is neglected with respect to x. So actually the horizontal asymptote, and we said this before, your vertical asymptote, you get it by equating the denominator to 0. So you get x is equal to minus 1 is a vertical asymptote. While if you take the limit when x tends to infinity or minus infinity, you got directly y is equal to 1. So you have a graph which is parallel to these two intermittent lines. And when x is equal to 0, it passes by this point here. So how does it look like? It should be something of this sort, nothing else. For the second one, for example, here you have when x equals 0, you get y is equal to 3rd, so it should pass by this point. Again, when y is equal to 0, x is equal to half, so it's also passed by this point. Again, it has a vertical asymptote at x is equal to minus 3. What else? It has also a horizontal asymptote when you x tends to infinity or minus infinity. You get minus 2, so it should also have this, or it has this horizontal asymptote. So now it should be parallel to these two lines and passes by these 2 points. How can it be? It couldn't be except something of this sort, like this. This is how it looks like. Again, suppose you have, for example, x over x squared minus 1. This is again simple because at x equal to 0 it should pass by this point, and it has two vertical asymptotes at x equal 1 and minus 1, like this. These are the vertical asymptotes at 1 and minus 1. The horizontal asymptote when x tends to infinity, you get y equal to 0, and this is an odd function. So what you draw here for x positive is similar for x negative, except that you change the sign. So what else? It should be something of this sort. It should go this way. But again here, since it passed by this point and this is a vertical asymptote, so it's like this. But again, it wouldn't go down because it's odd, so it should go up this way. And since it's odd, again, this is replica here, so you end up with something like this. So in fact, for these simple graphs, you neither use calculators nor software. You should be able to draw simple graph like this, and you watch out for the intersection with the axes, the asymptote. Usually the asymptotes is the key, the vertical and horizontal asymptotes. So now what are the general properties of graph? First, the symmetry. You should check for the symmetry here. If f of minus x is equal to f of x, your function is even, whereas it is odd when f of minus x is equal to minus f of x. It also, when you realize that f prime is positive, then your curve must be ascending, while it's descending when f prime is less than 0. Third property, the intersection with the axes. And actually, this is one good thing that you should do even from the start. When x equal to 0, you tabulate y naught. So the point 0 and y naught lies on the curve, on your curve. As well, when y is equal to 0, so your root, this is the point at which the curve passes by the x-axis. So the point c and 0 also lies on your graph. Again, the continuity. If you are considering algebraic functions, so most of them are continuous except the roots of the denominator. But in any case, you should try to check the discontinuity and continuity of your function. Again, your asymptotes, we said before that your vertical asymptote, you obtain it by taking the limit when x tends to a from the right or left. If this goes to infinity or minus infinity, then x is equal to is a vertical asymptote, while your horizontal asymptote, you obtain it by taking the limit where x tends to plus or minus infinity. If this is tends to a definite value L, so y is equal to this L or a, so y is equal to a is the horizontal asymptote. Again, the critical points. The critical points we said before. Your critical points should be interior points to the domain of f, at which f prime is 0 or does not exist. This is one point. You should make sure that these critical points are interior points first, and then f prime. If f prime is equal to 0 or they don't exist, the f prime doesn't exist, then this is a critical point. But this is not enough. This is sufficient. This is a necessary condition for the existence of your local extrema. But again, you have to check the sign of the derivative at, as we said before, at your before and after this critical point. And then your convexity. If the double derivative changed signs, and or the double derivative at a point around a point where f double prime is 0 or it doesn't exist, then this is an inflection point, and it separates between two regions of convexity and concavity. Now we come to some examples. Suppose I asked you to sketch this graph, the graph of this function. You have x plus 1 multiplied by x minus 2 divided by x plus 4 by x minus 3, and you wish to study the symmetry of this function. Of course, this function like this extends over R, except for the roots of denominator, which are minus 4 and 3. So actually, these cannot be critical points from the start because they don't lie in the domain of f. And they asked you to study the symmetry, the interval of increase and decrease, the intersection with the axes, the continuity, the asymptotes, the local extrema, all these property of function, and then they ask you at the end to draw the graph. Suppose we do this in detail. This is your function here. It is x plus 1 times x minus 2 divided by x minus plus 4 times x minus 3. And we take two orthogonal axes like this. And we start by studying this function. So the first thing is that you wish to your graph, is it symmetrical? No, it's unsymmetrical with respect to axes. So you overrule the study of whether f is even or odd. Now you get the derivative. Derivative tells you that y prime is equal to this, with the exception of minus 4 and 3. Now you of course, these two are not critical points, but you have some critical points where at point 7, at the point here now, at point 7, this is a critical point, and again at the point 9 there is another point here somewhere 9 which is another critical point. Now we wish to see whether at this critical point the function can have a local maxima or a minima. So what you do, you check for the interval of decrease and increase. You see directly that when you from f prime, you can actually check whether before minus 4 and after minus 4, etc. You see that your graph ascends always. So actually, and again, we said that this is not critical point. At this critical point, what happens? At the critical point, 0.757, we see that it ascended, it descended. Then this is a maximum. So we can say that at the 0.757, it's a maximum. Of course, this is precluded as well. And you end up with the point 9.25. You find that f prime descended, ascend. So actually, this is a minimum. You get a minimum at 9 and a maximum at 0.7. So we come here. We say this is somewhere here. This is a maximum, and this is a minimum, and this is a maximum. And then we move forward. Here again, the curve cuts the axes at the point when you put x equal to 0. You end up with y is equal to 1 over 6. It means that the point 0 and 1 over 6, your curve passed by this point. So it's easy. At the point here, 0 and the curve must pass by this point. And again, the curve passed by this point, and at the x-axis, yes, and also it passed by the point minus 1 and 2 by the x-axis. Why? When you put y is equal to 0, like this here, when you put y is equal to 0, you end up with what? Minus 1 and 2. So the points minus 1 and 2 are points lying on the curve of the axis of the function. So in fact, you have the curve passes by these three points, and actually this helps you very much. And this is a maximum, so it must be something like this of this sort. It couldn't be otherwise. Yeah. Again, the function is rational, and it's not continuous at minus 4 and 3. You keep moving. This we know. The curve has two vertical asymptotes at minus 4 and 3. Yes. Why? Because from here, directly, when x is equal to minus 4, when you take the limit when x tends to minus 4, light or left, and same thing for 3, you get a vertical asymptote. And you said before, a vertical asymptote, you obtain it by equating the numerator to 0. So you get x is equal to minus 4. This is a vertical asymptote, minus 4, and x equal to 3 is another vertical asymptote. So now it's clear that it should go this way and that way. Whereas here, had this function has a horizontal asymptote, if you take the limit when x tends to infinity, yes, indeed, because you have here x squared in the numerator and x squared in the numerator. So in fact, when you take the limit when x tends to infinity or minus infinity, you get 1. So you end up actually with something like this. It should be something like this. So this is the horizontal asymptote. So there is nothing left except that your curve must go this way and must go also do this. Your curve do this. There remains something. There is one point here at 9 point something here. So there must be a way to understand why it is a minimum. So there is no other way except it must be this way. For example, it might go this way. In other words, it reaches a minimum at 9 and then it goes again to 1. As your horizontal asymptote, it must tend to 1. So there must be a point of minimum here. And in fact, there must be also an inflection point somewhere here. Why? Because it has to tend again to 1. So after your point 9, there must be a point at which it changes from concavity to convexity. Here the curve is convex, and here it is concave, and here again it is concave. Whereas here it must be convex. So if we go forward after you realize, after you obtain your horizontal, these are your vertical asymptotes, because it tends to, the function tends to infinity at x equal to minus 4, tends to minus 4 from the right and left, as well as from when x tends to 3 from right and left. And your horizontal asymptote, you take the limit when x tends to infinity or minus infinity, you get equal to 1. So finally, all you now want to know from the derivative, now the value of your critical, we know the critical points at 0.7 and 9. So you substitute this in f of x to obtain 0.2 and 0.89, meaning that your local maximum is 0.2 and your local minimum is 0.89. These are the values here. This must be 0.2 and this must be 0.89 on the value of your function. And this is 0.89. So there remain now the second derivative. For your second derivative, all you do is that here is the function. And in fact, it coincides very well with what we draw. And in fact, we were better than the slide here, because here it shows as if it goes asymptotically to 1. But what in fact we discovered that there is some point after 9 here that it has it must have an inflection point without even considering the sign of the double derivative. Why? Because since it goes beyond y is equal to 1, so it must revert again to the value 1. So it must change from concavity to convexity, and there must be some point at which the double derivative is equal to 0. So this is your graph, and if you consider your second derivative and you construct again, this is your second derivative. derivative. It's quite long. If you construct your graph, you find that, in fact, it's concave, as we said, as we remarked here, and then convex, and then convex, and then again it becomes convex, from concavity to convex. So there must be a point at which the function, which is 13, it lies in the domain of f, and the function and the graph changes sign from positive, the double derivative from positive to negative. So it means it changes from concavity to convexity. In other words, 13 is your inflection point at which the function reaches a value of 0.91. And actually, this is how you draw functions, the graphs of functions. Very simple. The most important thing, your asymptotes, your intersection with the axes, and these actually the main points. And then again, the local extrema and the inflection point, this comes later. But from the beginning, if you know these first values or features, then you may like to draw directly the function, and then you wait for a little precision if you wish to pursue finding the local extrema as well as the inflection points. Now suppose you wish to study the graph of this function. Here, this function here, y is equal to mod x over x minus 1. Again, this curve is not symmetrical with respect to the axes. It looks what? It looks, in fact, continuous, except for x is equal to 1. And in fact, this is directly a vertical asymptote. Why? Because if you take the limit when x tends to 1 from right or left, you get this equal to infinity. And of course, also it has a horizontal asymptote, but because if you take the limit when x tends to infinity, you get 1, minus infinity, you get minus 1. So actually, this is an interesting curve. Now, this is the derivative. It tells you directly that your derivative does not exist at the point 1. But again, 1 does not lie in the domain of the function. So this is not a critical point. So there remains the point x equal to 0. So it tells you that at x equals 0, this is a critical point. You remain to know, to understand the sign of the derivative around this point, whether it changes from negative to positive, etc. In fact, you can do it right-click here. When x is negative, you get what here? You get here positive, negative, negative. When x is negative, this is negative, and this is negative. So it's positive. So it changes from positive to negative. It means that this is a local maxima directly. But anyway, we proceed. So your intervals from your derivative, you get directly the curve ascends from minus infinity to 0 and then descends. So as I anticipated before, this point is a local maxima. Whereas at the point 1, it descends all the time. It's not important because this does not lie in the domain of the function. So you have a local maxima, now only one local maxima at x equal to 0. Also, the curve passes by the origin. Why? Because it is from here, you have a mod x divided by x minus 1. So the curve passes directly by the origin. This is one thing. As we said before, it has an asymptote as x equal to 1. It also has two asymptotes, one y, when x tends to infinity at 1 and minus 1, like this. You have a horizontal, because if you take the limit when x tends to infinity, you get 1. When x tends to minus infinity, you get minus 1. You have a vertical asymptote. It passes by this point, and this point is a local maximum. So it should be like this here, without thinking. And again here as well, it changes as we find out sign between positive and negative. So it must be like this. What else? This is the vertical asymptote, so it must be like this. Is it in fact like this? We're going to see. So the function is not continuous at x equal to 1. The curve has a vertical asymptote, x is equal to 1. This we know. And two horizontal asymptotes, yes, when x tends to 1 from left. No, this is a vertical asymptote. When x tends to 1 from left, you get minus infinity, correct? And this is from the right-hand side, infinity. Two horizontal asymptotes, you obtain them by taking the limit when x tends to minus infinity and infinity. You get minus 1 and 1. So again, it's compatible of what we have seen. So there remain the point x equals 0, the only critical point, this we said before, at which f prime does not exist. It's a point of local maxima. F prime does not exist because we said critical points are the points at which interior points to the domain of the function, at which either f prime is 0 or does not exist. In this case, the derivative does not exist, but you have to check the sign of the derivative around this point, and we found out that it's local maximum because it changes from positive to negative. The value at this critical point, the value of the function is 0 because you put x equals 0, you get 0. And again, this is your function. Actually, it's compatible of what we have just reached. And this point, in fact, is a corner point because you remember if you obtain the derivative, you get what? You get the limit from left and right, 1 and minus 1. So it means this is a corner point. From the second derivative, you get something like this. Your curve is concave. And in fact, yes, it is from minus infinity to 0. Here, yeah, this is it's concave here. It's convex here, and here again it is concave. Yes, and the only inflection point is 0 and 0. Actually, this is inflection point also, which is nice. It's a point of local maximum. It's an inflection point. Why it's an inflection point? Because the second derivative does not exist here. But again, the second derivative, since it changes from convexity, from concavity to convexity, so we said that you get an inflection point, points at which your second derivative either is 0 or does not exist, and you have a change of sign of the second derivative. So this fact, in fact, this is a point of local maxima and an inflection point. Suppose, for example, we wish to revert to, for example, something of this sort. X, this is x divided by, for example, modulus x minus 1. Would this be different than the function that we just studied? No, it wouldn't be much, in fact, different. Because here, again, you have two vertical asymptotes at minus 1 and 1. And then you have also two horizontal asymptotes. No, we better take another. Your function is x divided by mod x minus 1. So in fact here you have a horizontal asymptote, 1, another one at minus 1. You have two vertical asymptotes like this. So how directly, and your x equals 0, it passes by this point. And if you wish to take the derivative, you get something like directly minus 1 divided by mod x minus 1 square. And since this is a horizontal vertical asymptote, so it must be like this. Your function actually it's odd, so it must, and this is a vertical asymptote, so it must be this way. Since it's odd, it must go this way. And here it is like this. So in fact, you need not pursue later. In other words, the difference between this one and the other one is that the other one was not differentiable at x equals 0, yet this one is differentiable because your derivative is equal to what? Is equal to minus 1. And if you get the second derivative, you will find it that this point, in fact, you have a first derivative, but you don't have a second derivative. And so actually, this one may be, again, an inflection point. But in any case, curves look different each time. But all you have to do is that you watch out for your function, and you stick to what? To a certain feature at the beginning. You stick to the vertical asymptote because your curve directly is parallel to them. You stick to the point of intersection with the axes, either with the x-axis or the y-axis. And we see for this example, even if we didn't pursue your problem, you directly can foresee how it's going to look like because you have two horizontal asymptotes and two vertical asymptotes. So there is no other way except that it will go like this. And then here, since it is this is a vertical asymptote again and passed by the point 0. Of course, it may revert back to minus infinity, but since it's odd function, and therefore it will go this way. And then you may pursue later trying the first derivative, and you try the second derivative. You'll find out the second derivative does not exist here. So this is a point of inflection because it changes from concavity, from convexity to concavity, or from concavity to convexity. And here it's concave. Again, this is concave. This is convex here. And that's it. And in fact, this is the way how you deal with graphs in general. There is no fear of dealing with drawing graphs of functions. You just wish to follow a set of systematic procedures, and you end up with exactly drawing your graph. So there is actually nothing to be concerned with, you don't need even to use machines or using software. You can just directly come up with your graph very simply, because actually all you need is that you wish to do some kind of croquis, some kind of schema, some kind of crude investigation of the features of your graph. You need to know how it does ascend or descend, or it changes sign, or it reaches maximum or minimum, or it has an inflection point. You don't need more than that. And for the simple graph, like we've seen before, like for example, x divided by x plus 1, or x divided by x plus 2, or all these kind of trivial functions, it will be a shame if you don't draw them offhand like this, very simply. In this actually lesson, all we spoke about are the meaning of the graph of functions. We said that we have to follow a set of systematic procedures in order to, and this systematic procedure, it has to be you have to check one by one whether it is even, the function is even or odd, whether it's continuous, whether it has a vertical asymptote and horizontal asymptote. It may have also oblique asymptote, but we didn't investigate this in these examples here. All you can check the degree of the numerator. If it is higher by 1 than the denominator, you get a vertical and oblique asymptote. You also wish to consider the critical points. These are points in the interior. There are interior points in the domain of the function at which the derivative ceases to exist, or it's equal to 0. And then you check the sign of these derivative around this point. And then if you wish to go further, you are skeptical about a region in which you feel that there is some kind of you wish to investigate more your graph in this region. So you may, for example, calculate your second derivative, and then you check whether you may have an inflection point, and that's it. And this is how things go very simply for drawing graphs. With this, actually, we come to the end of the application of derivatives. This is the last lesson concerning the application of derivatives. And in fact, there are so many applications. For example, there are polar coordinates. There are ways of finding roots of functions. The application of derivatives are vast. Not only like we have displayed before, L'Hopital rule, for example, or the maxima or minima, local extrema or absolute extrema of functions. There are so many applications concerning application of derivatives. In fact, any varying phenomena, you would find application of calculus. So these are only a set of examples that we wish to have talked about with you. The main ones concern the most important application of the derivatives or the process of differentiation. And there remains in our next, with this, we end up the first part of our series of lessons, and we start in our next lesson, hopefully, the second part, which is part of the course, which is integration. And before I leave you, I wish to remind you that this lesson, together with the remaining ones, and hopefully, and the one that have preceded, all are uploaded to the site of the MedNetU project, which is managed by the Consortium Nettuno, in order to subscribe for those students which are interested in pursuing a degree in education, whether in mechanical or informatics, in the Mediterranean area. So until we meet then, I wish you good luck. And next time, as I said, we're going to speak about different subject, which is the second part of our series of lectures on calculus, which is the integral calculus. So we finished differential calculus. Now we shall begin, hopefully, the subject of integral calculus. So until we meet, I thank you very much.